Hello. All right. I'm not sure when we started, but I'm broadcasting today a lecture for an intended audience, a small intended audience, but sharing this on my YouTube channel because I thought folks might be interested. It's a fun story. So back in the 1930s, Heinz Hopf found this remarkable way to take a three-dimensional sphere and assign continuously to every point in the three-dimensional sphere, two-dimensional sphere, which was essential, which was not deformable to just taking, say, the same point in the two-sphere for every point of the three-sphere. It's called the Hopf map. In 1947, J.H.C. Whitehead wrote down an integral which let you get another proof that that map was in fact essential, we call it. And the interesting thing about that paper is, so it appeared in the Proceedings of the National Academy of Sciences. In other words, it was for the consideration of chemists and physicists and biologists as well. And if you look at the citations of that paper, there are many more in the physics literature than in the mathematics literature. And I know this because I'm actually one of the folks who cited this from the mathematics literature. A lot of my work on Hopf invariants are really direct generalizations of this integral. Well, it turns out that some of the people in the physics literature who have been looking at this integral are on our campus at the University of Oregon, and they've generalized it, and we're working together. Some folks, one of my graduate students and I are working with one of those faculty and a group of their students, the mathematics together for some new kind of magnetic materials integrals, Hopfions, we're calling it informally. And I wanted to help the physicists along with the perspective that mathematicians have on de Rham theory, because I think this will prove useful. And again, I think others might be interested in this perspective as well, because the idea is, I mean, there's some great texts out there. I learned from Munkris. I think I learned that from him giving the course, from his book, Analysis on Manifolds. There's a book from Calculus to Cohomology, etc. So this is fairly standard material. I'm sure there's other places as well. But it's maybe especially as a physics grad student, it might be a little bit daunting to say, okay, try on your own to internalize this book, which takes a quarter semester to get through. So I'm going to we're going to have discussions, but I'm going to prime the pump with some lectures. So this is a crash course on de Rham theory with an eye towards understanding eventually the Whitehead's integral for the Hopf invariant. So what is de Rham theory? So de Rham theory is concerned with, I think of it as primarily concerned with integration, as well as differentiation. In particular, that relevant to geometry. And that's in all dimensions. And in particular, and especially on all manifolds. And I might, in a further lecture, just sort of revisit a little bit the definition of manifolds, but these are smooth shapes. So you don't want something like an X or a cone. You want like a smooth surface, but it could have, well, in dimensions, as we say. And it can be abstract, but the mathematicians will notice that I'm going to stick with, manifolds for me are going to be submanifolds of some Euclidean space. So I'd like to start with the basic example, which you don't need de Rham theory, and we're just going to go from here to build de Rham theory. And that's integral of a vector field along a curve. And so what's the setup? I've got some, we're going to be in R3. I've got some vector field V. So you've got V at a point is, we'll think of it as a column vector. So some quantity A at a point, or maybe I call it A of P, B at a point, or C at a point. So really a vector field is three functions if you want, but of course, even though that's exactly the right data, you can, you want to really start thinking of it slightly differently than you might just three unrelated functions. And I've got some gamma of t, which, well, more basically, I've got some curve C, and gamma of t is some choice which parameterizes C. So I've got some interval from R to S, and gamma of t is three functions, x of t, y of t, z of t. So already we see that three functions can have fairly different roles. Well, the first is a function which takes a point in R3 and gives a point in R, and this is each of these are functions from R to R, really making a function R3, and so we want that the image of gamma is the curve C, so it's some choice like that. And then remember that the integral of the vector field over the curve ends up being the integral from R to S of, I'm going to take derivative of these three functions. I'm going to take the dot product with the vector field. At that point. And then so for every t, I get a number, t between R and S, I get a number, and I'm just going to integrate that. Okay. So, so people who've been versed in mathematics would say, wait, I made a choice. I was supposed to start with, look at the notation, I'm integrating something over C, yet we have this gamma that's part of this data, these x, y, and z functions. And so, I will leave it as an exercise, it's a proposition, that this, we get the same number for any choice, with any choice of gamma. So it doesn't depend on the parameterization. And the magic there is the chain rule or U substitution. But the point is that that this is sort of integrating something geometric, this vector field. It's supposed to be somehow, force as I move along C or something like that, or energy or work, maybe. It's probably work integral most basically. So in any case, it's a basic kind of integral we'd study. And the point is that in de Rham theory, we pay attention to the role of the vector field. Not just that it's a vector field, but to what the vector field is being asked to do. And what that vector field is being asked to do is to take a tangent vector, just some curve, and produce a number. And the way it does it is with the dot product. But this is the essence of what both what the vector field is doing, and this is what we would call a one form. Is something which takes a tangent vector and spits out a dot product. Again, the vector field does that by the dot with the, sorry, takes a one form takes a vector and spits out a number. The vector field does this by the dot product, which in fancier terms uses a standard inner product on Euclidean space to identify a vector with a function on a vector. And this gets, it sounds pedantic, but at the end of the day, you realize that conceptually you're much better off if you understand really what the roles of objects are, and in some cases, whether you're really meant to be a vector or you're really meant to be a covector, a function on vectors. So differential forms, let me go ahead and what do? They take sets of in vectors, or some in, one type of, a one form will take one vectors, a two form will take two vectors, and once you've determined how many vectors you take as input, you're not allowed to change. Take sets of in vectors and spits out numbers. And really, this is for purposes primarily of, at the end of the day, integration. So taking total amount of some quantity that depends on a set of vectors, most basically in geometry. Things, integration to calculate length, area, volume, but really it's a flexible theory that can let you model many more general phenomena than just classical area or length. So if I go back to what I'm trying to do, namely in the case of the one form, take a vector and spit out a number, I can do this. I can do this by, I can say a vector goes to the length of its orthogonal projection onto the x-axis. And by the way, there's some linearity or multilinearity as well. I haven't said it yet, but we'll make it a little bit more formal later. But I'm just taking this first pass at it. Um, we call this this one form dx. Exercise, if you will, that's we can recover it from this kind of vector field if the vector field is just pointing purely to the right with unit speed 100 everywhere. We'll recover this through the dot product. But you notice that the language is just different. I want to take a vector and spit a number by projecting it onto the x-axis. And yeah, so the claim is that the previous example, so there's obviously, we can talk about dy and dz. The previous example we can write as the integral of c over a dx plus b dy plus c dz, where a, b, and c are these functions of p, which I could write. Sometimes we would even write okay. So let's give you a higher dimensional example now. A surface integral. And what a surface integral should be is of a two form. A two form should take two vectors and multilinearly and anti-commutatively spit out a number. So we've got to write that down in two form. Takes v1 and v2 as a pair. And spits out a number. And it does so linearly in each variable. And it also does so that so the number that v2 v1 goes to would be the -1 times the number that v1 v2 goes to. So what's an example? So if v1 and v2 are in R3, we can send them to the signed area of the parallelogram obtained by orthogonal projection of v1, v2, and their sum onto the and of course 0 onto the xy plane. Okay, so you can just take two vectors, project them onto the plane. They their shadows are two vectors in the plane. You take their sum, you get a parallelogram with this is going to be at the origin. And I'm going to take the signed area where the sign is going to be plus if, say, v1 it has a smaller angle than v2, so to speak, or minus if the opposite. So in particular, if like v1 is here, but v2 is down here, this will be a sort of a minus sign on that. And another exercise explicitly, if our VIs are all of the form AI, BI, CI, then this area is determinant of this little 2x2 matrix. Okay, those are the two projections. I take that area, it is given by the determinant. The determinant does have a sign like that. So you could also say this is just the cross product of V1 and V2 dotted with the vector 0, 0, 1. Okay. So this is called this project and take area. This whole way to take two vectors and produce a number is called dx dy. Okay. And it's, by the way, minus dy dx. So again, these signs are important, and the way we write our order of variables becomes important because of that. So then any two form on R3 can be expressed through these coordinate projections. So as a dx dy, and again, sometimes I'll put the wedge there, sometimes I'll forget, plus b dx dz plus c dy dz, which if I did things correctly, there's a more familiar way to maybe express this. What I'm going to do is I'm going to take my two vectors and produce a number by taking their cross product, but then dotting that with the vector c minus b a. Okay. Didn't set things up to sort of make things appear in the order that you'd expect. I'm pretty sure this is right. Again, think of this as an exercise that that this cross product dot with that vector is just taking us to the sum of those three areas, projecting our two vectors in the three ways that we're familiar with in R3. Okay. So these quantities can be integrated over surfaces. So again, this I talked about it as like it's a single way to take two vectors statically, but then what you do is you let the functions let a, b, and c not be numbers but functions. Oh, sorry, shoot, I'm overusing a, b, and c. I should have here. Let me go ahead and uh, and change these so that I'm not overusing. I'm also trying to be consistent that A, B, and C are coefficients of forms, and X and Y are spatial coordinates. But again, that's sometimes hard to be consistent around. So then this should be X1, Y1, X2, Y2. And this would be V1 cross V2 cross 0, 0, 1. Okay. Right. So these quantities can then be integrated over surfaces. And let me take you through in coordinates first, give you a picture. So I've got some surface. Maybe it has a couple of boundary components. Maybe it has some interesting topology. And what I now do is, well, one thing is I can't parameterize by a single, before I was parameterizing everything by an interval. Now I would need to parameterize by a subset of R2, but this curvy surface up in 3 space can't just be, there's no subset of R2 that folds nicely on it. Well, there is, I could slice it, but that's inconvenient. It's much better in general to think about inside of R2. I can take little squares and, or other shapes and parameterize parts of the surface. And that's our, I'll still call that gamma. And I've just got some X, which I'll call these coordinates T and U, X, Y, Z, which depend on T and U. And I've got my omega is a 2 form, and the integral, so omega a 2 form, a way to take 2 vectors and produce a number, and the integral over my surface of omega, so this is my surface S, is going to be, well, I'm going to have to take some sum over the integral over these, the T and U in these patches. So I'll have to take lots of patches. It's like a patchwork quilt. Often, sometimes you can figure out a way to do it with not so many patches. And what is omega going to do? It's going to spit out a number from 2 vectors, and those 2 vectors are going to be just the derivatives of these parameter functions with respect to T, and the derivatives of these parameter functions with respect to U. And geometrically, what those vectors are, let's just call it sort of gamma prime in the T direction and gamma prime in the U direction, is if I take a unit vector at a particular UT, I've got my standard unit vectors, and let me make them 2 different colors. So I've got my parameter space is R2, so there's a sense for what my standard vectors are. They could map in some crazy way here. Maybe one is very, very big and one is very small, and maybe their order changes. Before it was sort of right-handed, now it's left-handed or whatever. That's fine, but those 2 vectors are then what omega is going to eat and spit out a number. So really what we're saying is this is going to be some sum over these integrals over these parameter patches of omega is going to take this gamma T prime at T and U and gamma prime in the U direction at T and U, and spit out 2 numbers. Sorry, and spit out 1 number. It's going to take 2 vectors, spit out a number. That's what we integrate over the square. And so an example, that's in general what an integral of a 2 form over a surface is going to be. And a key example is when omega is given by V1, V2 goes to V1 cross V2 dotted with some fixed vector V, or as things vary, that would be some vector field. And in that case, this V, maybe I'll put it in red or something like that. This vector field V, we're taking the cross product of those two things and then dotting with it. And of course, that vector field V, then if it's tangent to the surface, it's going to be a linear combination of those two gamma primes. And so it's going to, when dotted, I'll get 0. But if it's going through the surface, I'll get a large contribution. And this is this integral. So in this case, the integral over the surface for this omega calculates flow or flux of V through S. So that should be fairly familiar example or exercise to work through that example and double check that this agrees with how you understand flux or flow. And again, all we're doing here is taking these coordinate formulas, the cross product, and then dotted with my vector field, and saying what those cross products and vector fields are doing. Well, the is just a way to take those two vectors that are tangent to the surface and producing a number. Of course, it also depends on the vector field, but if I fix the vector field, then it becomes a way to take two tangent vectors and produce a number. So, so K-forms, let's start again. K-forms on some subset of Rn generalize this. What you need is you need some way. So you've got your basic dx1 wedge, dx2 wedge. Instead of xyz, we switch to x1, x2, x3, etc. And the form, again, we generally want this to vary. So I've got some function on Rk, and I'll call it f1 ... k. And then, and so I'm going to project onto the first k coordinates, and I'm going to multiply by this number f evaluated at that point where I'm thinking of the form to be evaluated at. And then that's just one part of the story. Of course, I can project onto not the first k coordinates, but the first k minus 1, along with maybe the k plus first coordinate. And then I've got some function for decorating that, but really just think the projections here are what makes the sense. And basically this is just this continues as you might think. So in coordinates, it becomes a lot to keep track of. You have to keep track of which subspace of Euclidean space, a generalization of the axes or the xy plane, xz plane, etc. That becomes a little bit more cumbersome. And right. And then we can take, and we might say more about this in some more detail. Define, I'm not going to yet, but the whole point is we can integrate such an object, if this is our omega, over when M is a k-dimensional submanifold. of Rn or of whatever subspace. And the reason I'm saying that is the domain of definition is important. So the domains of definitions of these F. Maybe I'll just call it F sub S for whatever subset I'm looking at. Or I'll just call it F's. The domains of these functions, which are telling you what multiples of my projection length to take. Domains of these F's are important. So on R2, but take away the origin, there is something which we call d theta. We'll come back to why we're using that name, which is just on R2, it's simple. There's only a dx and dy, and then a wedge dx wedge dy. So you can take minus y over x squared plus y squared. That's a function on R2, but not defined at the origin, and multiply that by dx, and then also take x times over x squared plus y squared and multiply that by dy, and you get this function d theta. It's not defined on all of R2. So it's not defined at the origin, and eventually we'll sort of see that that's a reflection of the topology. Its behavior is going to start to reflect the topology of the domain of its definition. Somehow this form absolutely can't be extended to R2. Its properties would fail substantially if we tried to extend it there. This is a wonderful thing because it's integral over any curve of omega is, we can take this to be a definition of, but is the winding number. Again, let's maybe make this an exercise. So if I should double check, I think I've normalized it to 2 pi. So the integral, let me give you some examples. Integral of c omega equals is going to be 2 pi if, for example, c is the curve that, if this is the origin, maybe the curve that goes like this. Doesn't have to stop and end at the same place. It's just going to be pi if I make it halfway around. I can go around more than once. I can make it all the way to, say, 4 pi if I wrap around a couple times. If I don't wind around at all, and you might, you can try to fool it. You can try to maybe go around and then back, and notice that, and here I'll draw where the origin is, because that becomes important for all of these. So this is some integral that that calculates your progress winding around the origin, and if you form a closed loop, it really will be exactly the number of times you wind around the origin. Right. So now let me talk a little bit about differentiation, because I want to get to one of the main, talk about where we're going to go. So forms are things that can be integrated, but we're going to see that they can also, in interesting ways, be differentiated. And differentiation is going to sort of change the nature of the form. A form is something that takes k vectors and produces a number. Its derivative will take k plus 1 vectors and produce a number. So let's go back to R3. a zero form is just a function. Because I'm just, for every point in R3, instead of taking 1 or 2 or 3 tangent vectors at a point and producing a number, I'm taking 0 vectors and producing a number. Oh, so for any point in R3, I've got a number. That's our friend, the function. So if f is defined on some subset of R3, then it's a function R3 or a zero form, then df is going to be the following. I'm going to take the derivative. Everything's smooth here, by the way. All derivatives exist to all orders. I'm going to take the derivative of f with respect to x. That's another function on all of R3 or on the subset that f is defined on. So f is on some subset of R3. And that's the number that I'm going to use after I then project onto the x-axis and take length. I'm going to scale it by df dx, and then I'm going to do the same thing in all 3 coordinates. Okay. So then this is a fun one. And again, this will be an example or exercise. The integral over a curve of df is just going to be, I'm going to say it's from P to Q, is going to just be my f evaluated at P, or sorry, Q, minus, if I'm going from P to Q, minus my f evaluated at P. All right. So this will be, this is a first case of a big theorem that we're going to spend some time discussing. We won't get the full proof. These kinds of one forms, we call this an exact one form. Yeah, you're exact if you are the derivative of something. And then another exercise, the first exercise should be simple enough. Another exercise is show that the one form given by sending v to the number that I get by taking v dotted with the gradient of f is another way to say this one form df. And that means that under this relationship between forms and vector fields, a conservative vector field corresponds to what we just called an exact one form. Okay, I'm going to just give you a taste of the next one, the next thing to think about. So I just gave you the derivative of a zero form as a one form. I just took the derivatives, partial derivatives, and used those for my projections. These first 2 exercises might show you why that's the right definition, give you a start to show you. What if I have a one form? Well, if I want to take a dx plus b dy plus c dz, remember these are all functions defined on some, and take d of that, that's going to be equal to, there's going to be a rule. I'm going to go ahead and follow it pedantically, and I won't write everything out. Another exercise, if you want, is go ahead and write everything out to yourself, for yourself. So I'm going to take all partial derivatives, and every time I take a partial derivative, I've got a d whatever, the variable that I'm taking derivative with, and I stick that at the beginning. So, and there's some rules here. Dx wedge dx is 0. Basically, at this point, the xx plane is just the x-axis, and there's never any area to get when I project onto the xx plane. That's sort of an informal explanation why that should be so. These terms will also be 0. Also, dy dx and dx dy differ by a minus sign, so this ends up being partial a with respect to y minus partial b with respect to x. Sorry, other way around. Well, I'll do it this way. Dx dy, and there'll be 3 more terms, each with 2 of those. So this is so then you notice, so this is some sort of, well, then what happens if, sorry about that. So that's just the formula for the derivative of one form. Shouldn't be terribly meaningful for you, but we just made 2 definitions. Let's see how they play together. So if I take d of a 0 form, so d of a function is a 1 form. I gave you a formula for that. D of that 1 form, I gave you this formula, and I'm gonna, so my A was partial f with respect to x, and my B was partial f with respect to y. And so by equality of mixed partials, we're in a smooth setting. This is 0. So that's kind of interesting. This D is telling me that if I happen to be this kind of conservative or exact 1 form, then D, my derivative is going to be 0. So now let me say a little bit about where we're going. These are all sort of exercises to go through at this level of just getting familiar with how these calculations go. And now let me tell you where we're going to go next time or so. So first, as I said in R3, we have functions are the same as what we're calling 0 forms. And I told you that there's a way to assign a vector field, sorry, a 1 form to a vector field. And in fact, every 1 form comes from a vector field in that way, through the dot product with the vector field. We also said that you can take a vector field and make a 2 form by taking the cross product of the 2 vectors and then dotting it with the vector field. And I claim that that's also an isomorphism. We haven't talked about 3 forms yet. But there's going to be a standard way, take a function, and that's just going to decorate the form dx, dy, dz, which is our sort of only 3 form locally. and then you've got the functions. And then in multivariable calculus, and then of course you use this in electricity and magnetism, you've got the fact that del takes a function and makes a vector field, del cross takes a vector field and makes another vector field, and del dot takes a vector field and makes a function. Well, what we're going to see is that all of these are captured by this one thing that we don't bother to give a different name. We call it D. And the reason is that there's just a fairly small set of ideas, that axioms, a seed that you plant, that defines D and then works across all kinds of forms in all ambient dimensions. So all dimensions within any ambient dimension. And so this is this sort of elegantly captures what you need to do integration in all dimensions. And by the way, you know, for my physicist audience, look, if you're doing even classical mechanics and you want to phrase things, I forget, I think this is the Hamiltonian formalism, in terms of both position and momentum, that's six-dimensional a priori. You're maybe looking at some subspace of that six-dimensional phase space, but you want to work in all dimensions a lot. I mean, hey, biology, you're keeping track of, you know, biomass and number of whatevers, and so we want to work across all dimensions. And this is one story that I'll try to tell, I think, next time. But I want to just say, you might think, okay, that's easy enough, and I'm a big fan of vector fields and things like that. Well, vector fields can still give you one forms, but I challenge you, two forms as we've defined them. The definition I gave you in R3 works. I'm just going to project onto the xy plane. I'm going to call that dx wedge dy. Project onto the xw plane if I go xyzw, and that's going to be dx wedge dw. But there's nothing that's sort of classical or familiar that you would call here. There's no vector field. There's also, by the way, a way to take a vector field and make a three form with some generalization of the cross product. But this is key. This is one reason why it's important to learn about forms. And then the other thing, and again, it's important that this is happening across all dimensions, is that across all dimensions, you've got this fundamental theorem. And this is true in two senses. It's both a fundamental theorem. We like to say that a lot in any theory. Hey, this is something we're going to use all the time. But it's also a generalization of the fundamental theorem of calculus. Some people would say it is the fundamental theorem of calculus, and it's called the generalized Stokes theorem. You could also call it the generalized Green's theorem, but nobody would understand. They would think that that's a funny choice because everybody chooses Stokes theorem to call it the generalization of. So now suppose W has boundary called boundary of W. We've seen examples. Our surface had circle boundary components. Our curves had endpoints. I'm just giving the notation. And this is all happening inside some Rn, but it's maybe a K form. Or sorry. And let's say that W is d-dimensional. And I'm going to let omega, so I'll have to be good about writing big W, little omega, is a d-1 form. Then the integral over W of d omega is equal to the integral over the boundary of W omega. And that's capturing Green's theorem, Stokes' theorem, and then just all of their generalizations across all dimensions. It's this lovely little formalism. So let me give you a central application. So if d omega is 0, it's closed, and the left-hand side is 0. And W is of the form M cross I. So it's something with boundary, but it's just a cylinder. So we've got two boundary sides. So let me just parenthetically remark that the boundary of M is empty. Then, right, as I said, the integral over W of d omega is now 0. So that's the integral over the boundary of M cross I. I is just the interval from 0 to 1 of omega. And that's the integral over M cross 0 of omega minus the integral over M cross 1 of omega. So basically, we're saying that these are equal. And so what this is saying is that you've got some kind of homotopy invariance of the integral. And that's homotopies large and small, but the point is that you do have a very strong invariance. Here, and I'll end with this final example. Take omega equals d theta on R2. Let's remember that this is, well, let me give it, d theta was this minus y over x squared plus y squared, comma, and that was dx plus x over x squared plus y squared dy. So exercise, show that d theta is equal to d of the arctan function. And there's a little bit of a lie here. The arctan function, I want to show this is on R2 minus the origin. The arctan function isn't smooth. I have to choose like some cut point, right, for arctan to jump 2 pi. But because I can choose that anywhere, there is a form of the arctan which is smooth at any point away from the origin, and I'll just use that same, and then you have to show that any choice of, you know, arctan plus 2 pi, arctan plus 4 pi, all those choices locally, the smooth functions have the same derivatives, and that is exactly this this minus y over x squared plus y squared dx, etc. So that's kind of fun. This is, it's not really an exact form, but it's almost it's d of theta. It's just that theta isn't really a function now. Theta is this multi-valued function. And then I want to show, that's one thing I want you to show. And then the other is to show that d of d theta is 0. And so what that would show you, applying Stokes's theorem, is that if I'm in a setting where I've deformed some curve, you know, let me maybe draw it over here. I've got some curve C0 around the origin or whatever. Maybe it's you know, we'll have to talk about what happens when you wrap around multiple times. We'll set this in a different way. But, you know, I deform it to some C1, and this is my M cross I up to reparameterization, then this winding number is going to be the same. So if I deform my two curves in ways that don't cross the origin, because I'm living all the time in R2 minus 0, then the winding number is homotopy invariant. And that I often think of as like one of the first real theorems in topology. it's, well, it's one reason I thought topology was kind of a funny thing to study when I first read about it a little bit in high school. Like that's completely obvious. The number of times I wind around the origin for a closed curve doesn't change if the curve kind of never crosses the origin, but it's actually harder to prove than you might think. And it kind of is this basic idea that then has these spectacular generalizations, some of which we'll talk about. Okay, that's where I wanted to end. Yeah,